in the next chapter, and I forgot the number of the module, but anyway, this is the next module, and this is on cogeneration and combined cycle. Okay, so there you go, like that. This chapter is actually not very long. It's an overview of these two classes of technology, which is actually gaining importance these days as we see more and more needs for better energy efficiency. So these two, the bottom line is these two technologies are already proven actually to be able to increase chemical processing plants energy efficiency. Okay, so this is not even though it may look like something sophisticated, but actually this has been around for several decades at least, and in some form or another. And it is gaining popularity again because the need, increasing need to improve thermal efficiency of chemical processing plants, and at the same time to reduce the carbon footprint or CO2 emission of process plants. Okay, so we like these technologies. We want to be able to incorporate them as much as possible in any chemical processing plants. Now, however, of course, you also have to remember that any energy-saving technology usually implies an increase in investment. So when we incorporate these technologies to our plant, usually our chemical processing plant becomes more expensive to build. But however, they will be less expensive to run. So there's always a balance between investment cost and operating cost. Clearly, these energy-saving technology will not save you the initial investment. In fact, you have to spend more money to build these systems. But once you have it up and running, it gives you saving in terms of energy cost. So it will save your operating cost. Yeah. And this is a prelude for next year, where you will learn about engineering economics. And more often than not, we will have to choose a balance between this, investment cost versus production cost or operating cost. Okay, or capital expense. A more popular term for it is capex and opex. Capex is a capital expense, and opex is operating expense. So we need to have a good balance of both. Okay, we in engineering, we oftentimes are dealing with conflicting demands or conflicting constraints. So it's quite common actually when we design a chemical processing plant, for example, or when we design a product. If we want to reduce the initial cost or investment cost, more often than not, we have to sacrifice the operating cost. Okay, so when we decrease the investment cost, it usually will impact an increase in operating cost, and vice versa. Okay, so if we want to reduce operating costs, typically we have to invest something. It's quite rare actually to be able to do both. Okay, reduction in investment cost and also reduction in operating cost. Okay, right, and that's what we do as engineers. We have to work with compromises. We have to work with frequently. We have to work with conflicting constraints. Okay, all right. So with that thinking in mind, let us take a look at these interesting technologies. Okay, cogeneration and combined cycle. All right. Go. So as you have learned in the previous chapters, production of work, which can then be used to drive other equipment or to generate electric power. Okay, by fossil fuel combustion is largely an inefficient process. Okay, so the thermodynamic efficiency typically for power plants range between 30 to 45%, which is pretty lousy actually. This means that between 55 to 75% of energy contained in the fuel, okay, chemical energy contained in the fuel is actually wasted as heat release to the environment in one form or another. Okay, so actually only less than 50% of energy contained in a liter or in a kilogram of fuel can be used to generate power or mechanical energy. Okay, so that's pretty bad. So we are motivated to develop technologies that can recover some of this wasted heat Okay, so approximately 80% of the heat contained in the fuel can be utilized. So if we include everything, if we include all of the energy saving technology, waste heat recovery technology that's available today, we can get about 80% of the heat or the chemical energy contained in the fuel. And that's pretty high. That's very high, actually. Okay, and these technologies include cogeneration and combined cycle. Okay, now these are two different terms. Even though the technology, the process equipment is quite similar between these two, but they are designed for different purposes. Okay, so cogeneration uses waste heat, okay, meaning the heat that otherwise be wasted in the environment for many different processes, such as space heating or drying. Okay, now remember, power generation, ya, pembangkitan tenaga listrik using various power plants will need to eject heat to the environment, right? That's just the second law of thermodynamics. And it is this waste heat that we try as much as possible to use for other purposes. Okay, for example, we can use it for heating, for process heating. Okay. All right, so that's cogeneration. So the basic concept in cogeneration is we're generating two outputs, two types of output: mechanical energy, which then we can use to generate electricity, for example, okay, or to drive other equipment, and heat generation. So we call that cogeneration. Okay, so another term for it is CHP, combined heat and power. Okay, so if you come across the term CHP in literature, is the same as cogeneration. It means that from a single process, from a single utility plant, we produce two things, right? We produce power, meaning it's either electric power or mechanical energy to drive other equipment. We call that power, and heat. Okay, right? So that's called combined cycle, sorry, cogeneration, or CHP, combined heat and power. Okay. The second class of technology is this one here, combined cycle power generation. Okay. Now the different thing is here, the main purpose of combined cycle is to produce power only. Okay, but it's using two different thermodynamic cycles to produce the same item. Okay, so this is one product, one basic product, which is electric power or mechanical power, but that power is produced using two different cycles that works alongside each other. Okay, combined cycle power generation is a two-cycle electricity or electric power generation that uses heat from the first cycle to run a second cycle. Okay, so commonly in a combined cycle, the two cycles are Brayton cycle, gas turbine, and Rankine cycles. Okay, that's not the only configuration, of course, but it's the most common type of configuration. So combining gas turbine and steam turbine. Okay, so basically the waste heat from the Brayton cycle, from the gas turbine, is used to boil steam, to generate steam, and to run steam turbines in the Rankine cycle. Yeah. Now, just to give you an idea, oh yeah, by the way, please note please note the diagram on the left-hand side here. This is called a Sankey diagram. Yeah. Let me write it down for you. Okay, so this is the Sankey. Sankey diagram. Okay, and it's very important for you to know what it means, what information it contains. Okay, Sankey diagram. Basically, it tells you, so this one here, of course, here the energy is 100%, right? So we start from 100% energy contained in the fuel. And then how much losses, what is the conversion, what is the energy balance? Okay, so the 100% energy contained in the fuel is converted to how many percentage of energy for each category. Okay, for example, here, okay, so what is the heat loss to the environment? Maybe this is like 60%, let's say. Okay, I'm just throwing up these numbers here. Okay, use in the power station, so own use, for example, let's call this maybe 5%, and so on. Now, you need to notice, you need to note the meaning of the width of these arrows. Okay, so larger arrows, thicker arrows, sorry, not larger, thicker arrows refers to higher fraction of energy. Okay, where is my cursor? I can't see it. There we go. Okay, so this one is thick, right? This arrow is thick, and it signifies a larger portion of the energy. Okay, so it's intuitive. I think a Sankey diagram is intuitive, but you need to know what it means. Okay, so thinner arrow stands for lower fraction of energy, smaller fraction of energy. Okay, so we don't just draw the arrow this way because of space available in your paper or something like that, but really the width or the thickness of the arrow signifies how much percentage of energy that we're talking about in a particular conversion. Okay, so for example here, loss and transmission, you can see that the width of the arrow is roughly the same as this one here, so we can say that perhaps, okay, so this is probably also 5%. And this one here, the amount of energy delivered to the customers, this one is pretty large, but it's not as large as this one here. Okay, so this is definitely less than 60%. You can also look from the width here. Okay, there you go. Oh, sorry, not that one. Erase that. So that would be, if we just look at the energy delivered to the customer, so the width is roughly like so. Okay, so you can sort of guess, you can sort of eyeball this, how many percent is this. Okay, you get the picture, right? So this is what Sankey diagram is. Okay, all right, and then here in the picture that I show at the bottom here, this is the picture of the same stack, of the same flare stack. Yeah, but the left-hand side is photographed by using a regular camera, visible light camera, and the right-hand side is photographed using infrared imaging camera. And you can, what I'm hoping to convey to you is, we need to appreciate the amount, we need to understand the amount of heat that we need to release to the environment and the need to reduce it as much as possible. Okay, so this is from just one flare. You can imagine how many flares are there in the world, right? So this is good for the environment. If we can extract as much waste heat as possible from a process, then it will be better for the environment. Okay, and that's what we do with these technologies. Okay, so let's take a closer look at cogeneration. And these are the two basic configurations of cogeneration technology. The left-hand side is called a topping cycle, and the right-hand side is called a bottoming cycle. Now, before we go to the detail here, let me show you really quickly why we call them topping and bottoming cycle. Okay. So, as I mentioned, cogeneration process, right? You're using only one thermal cycle. Okay. So again, please note that the main difference between cogeneration and combined cycle, as the name implies, in a cogeneration cycle, in a cogeneration technology, we only use one thermodynamic cycle. Typically, it is either Brayton or, not and, it's either Brayton or Rankine cycle. Sometimes we can also use diesel cycle, but it's not very popular. Okay, so we can either use Brayton or Rankine cycle. Now, if we draw those two cycles in the same TS diagram, okay, temperature versus entropy diagram like this, okay. So if we draw Brayton cycle and Rankine cycle in a single TS diagram, then the Brayton cycle, you know, with a typical condition, okay, typical condition for Brayton cycle, real life Brayton cycle oftentimes will sit on top of Rankine cycle. Okay, it operates at higher temperature. Okay, compared to Rankine cycle, that's why it sits on top of the Rankine cycle. Okay, And the term topping and bottoming refers to the power cycle, the power generating cycle. Okay, it refers to the cycle that generates electric power or mechanical energy. Remember, CHP, combined heat and power. Okay, so from one process, it generates two products, heat and mechanical work. Okay, again, when we say topping versus bottoming, what we refer to is the power generation part of the utility plant, not the heat generation part, but the power generation part. Okay, so if the power generation part of the cogeneration process relies on gas turbines, meaning Brayton cycle, then we call that configuration as topping cycle because it's located on top. Okay, because the Brayton cycle is located on top of Rankine cycle. Okay, conversely, if the power is generated by steam turbine, by Rankine cycle, we call the technology bottoming cycle because the power generation cycle sits below, it sits at the bottom. Okay. Okay, that's the meaning of topping and versus bottoming cycles. Okay. All right. Hope that's clear enough. So let's take a look at a more general description of these technologies. Okay, so topping cycle configuration. Yeah. Again, topping cycle means that we're using Brayton cycle to generate power. Okay, so this one here, the blue box here, will be definitely gas turbine. Okay, Brayton cycle. Okay, so let me repeat that. So this is a Brayton cycle, which converts fuel into electric power, okay, or mechanical power or whatever you need. Okay, bottom line is it produces shaft work. Okay, jadi ini yang dinamakan dengan siklus pembangkit daya, power generation cycle. Ya, dalam siklus topping, dalam konfigurasi topping cycle, maka yang di atas ini ya siklus pembangkit dayanya ini adalah siklus Brayton. Ya, siklus Brayton ini ya tentu saja wujudnya adalah turbin gas seperti yang sudah kalian pelajari. Ya, jadi pembangkitan listriknya atau pembangkitan energi mekaniknya menggunakan siklus Brayton. Okay. And then the waste heat in the exhaust gas of the turbine is used as thermal energy supply. Okay, so it is used as a thermal energy, as a heating media, if you will. Okay, okay, so the hot gas coming out of the turbine is used as a heating media in our process plants for various purposes, for heating of reactors, chemical reactors, as a heater for raw materials, whatever you need. Okay, if your process plants have heating duties that can be fulfilled by this hot exhaust gas, then you can build this type of topping cycle. Okay, right? And then there will always be, inevitably, there will still be some waste heat that has to be released to the environment eventually. But of course, we aim to minimize this waste heat, okay, by extracting heat as much as possible here. All right. Okay. Then the second one, the right hand side, this is the bottoming cycle. So here, the fuel, okay, the fuel is combusted to produce thermal energy first for the plant. Okay, so the fuel combustion is used to generate thermal energy for the plant first. And then the remaining, the residual or the leftover thermal energy is used to generate power. Okay, right? And more often than not, this will rely on, well, because this is already a waste heat. Okay, so you can no longer perform combustion on this. Okay, and usually the temperature and the pressure is too low for a Brayton cycle to work properly. Okay, so what we do here is we feed this hot gas, okay, to a boiler to generate steam, and then the steam then drives steam turbine. So the power generation cycle is not a Brayton cycle, but a Rankine cycle, this one here. Okay. Okay. Now, just to give you an analogy from our perhaps a more familiar technology. Anybody know what the turbocharger is? Have you ever heard of turbocharger?
Me personally, I haven't heard of it. Maybe others.
Have you ever ride a vehicle with a turbocharged engine? Do you know any vehicle that uses turbocharged engine? That's actually quite a lot, actually, on the road. Let me give you some example. Toyota Fortuner, Mitsubishi Pajero, Mercedes bus. Okay, so virtually all of the bus that we see every day in our cities, okay, bis kota, bis antar kota, and whatnot. So those almost all of the heavy trucks and buses in Indonesia now runs on turbocharged engine. Okay, now there are also some gasoline powered cars that use turbocharger. Kia Seltos, for example. Oh, yeah, by the way, a car that has been gaining popularity these days, Toyota Race. Okay, the Toyota Race, the 1 liter version, Toyota Race uses a tiny turbocharged engine, okay, 1000 cc engine that use turbocharger. Now, what is the purpose of turbocharger? Is actually it is an equipment added to the engine to increase the pressure of air coming into the engine, because higher air pressure will improve your power, will improve your fuel efficiency. Okay. Now, the things that you need to be critical about is how we can drive that turbine. Okay. So turbocharger, the way turbocharger works is we have a small turbine, a tiny turbine, okay, maybe about the size of this big, maybe, a tiny turbine that rotates at high speed, which compresses incoming air. Okay. So the question that needs to be asked is, what drives this turbine? Okay. What really drives this turbine? The turbine has to be moved by something, right? Okay. Can have anybody maybe have heard, or maybe some of you guys have read somewhere how an automobile turbocharger works? What really rotates the compressor turbine? Oh, it's a bit similar to what we have here, okay, in these technologies. So the force necessary to rotate the turbine, the compressor, sorry, the compressor actually comes from the waste gas, from the exhaust gas of the car, okay, or the trucks or bus. So the waste gas from the engine actually contains enough kinetic energy, it contains enough mechanical energy to rotate a turbine, okay? Just like you're blowing, you blow on a fan, on a toy fan, and then the fan rotates. That's how the turbine works. Okay, so this tiny turbine is inserted into the exhaust line ke dalam saluran gas buang ya, knalpot, and then this waste gas, the pressure from the waste gas, then rotates this turbine. The turbine in turn rotates the compressor. Okay, so this is one way to utilize waste heat or waste energy. Okay, but rather than driving a turbine, here what we have here, okay, so the thermal energy from the process plant, okay, it does not contain enough mechanical energy to be directly used in a breathing cycle, but it's hot enough to generate steam. So that's why we use this thermal energy, this waste thermal energy, to generate steam, and then the steam drives the electric generator. Okay. All right. An example in the process technology, an example of bottoming cycle is the use of flue gas from steam reforming section, for example, in ammonia plant, to produce steam in waste heat boiler. This is a pretty catchy term here, WHB. So WHP is waste heat boiler. This is a pretty popular equipment in chemical processing plants as an effective way, as an efficient way to utilize heat that is normally wasted to the environment. Okay. Now, note that there's more to just the need to save energy when it comes to motivation to include these technologies in our processing plant. Okay, so now let's go back to our previous slide. Okay, here, well, this is not really a good example, but you can start to appreciate hopefully the amount of heat that needs to be released to the environment, and also the temperature of the waste gas. Now, temperature of waste gas is actually regulated by governments. Ya, jadi gas buang ini nggak sembarangan. Ada aturan dari pemerintah yang menentukan temperatur maksimum berapa atau level of radiation-nya ya. Jadi berapa tingkat laju radiasi maksimal yang diperbolehkan. Intinya sih kita nggak bisa sembarangan aja membuang gas buang ke lingkungan. Kita harus upayakan supaya temperaturnya serendah mungkin, ya, tanpa mengganggu prosesnya. Oke. Jadi motivasi untuk memanfaatkan sebanyak-banyaknya panas buangan itu bukan hanya untuk mengefisienkan penggunaan energi, tetapi juga untuk mematuhi peraturan lingkungan. Okay? Because flue gas from steam reforming section is actually very, very hot. This has a very high temperature, and you will most definitely violate environmental regulation if you just eject the hot gases from a primary reformer to the environment. Okay, so one of the way to reduce the temperature and also generating energy in the process is by using these WHPs. Okay. All right, we have discussed this one. This question here, I'm gonna save this as your own exercise. Okay. Do search for this in the internet or in your references anywhere. The reason why topping cycle is more popular than bottoming cycle. Okay, why around the world there are more topping cycle plants compared to bottoming cycle plants. Okay, so there's an easy explanation for this. Okay. Okay. So this is what we call a self-study portion of your class. Okay. So your university students, you're no longer high school students, so you are expected to be more independent, more self-motivated in learning. So when we throw questions like this, don't just leave it like it is, but try to explore why. Try to find the answers to these questions. Okay, we're throwing breadcrumbs to you, and so this is a good way. This is a good way to learn to really understand the concept of thermodynamics and how they apply to real life chemical processing plants. Okay, or also power plants. Yeah, by the way, don't get confused between power plant that is designed as an integrated part of chemical process plants versus power plant that stands alone, operated by PLN, for example. Oke, ya, jadi jangan bingung. Yang namanya power plant, ya, pabrik pembangkit listrik itu bisa saja dibangun sebagai bagian yang terintegrasi dari suatu pabrik yang besar, pabrik kimia. Atau memang dia berdiri sendiri sebagai suatu perusahaan. Itu biasanya misalnya pembangkit listrik yang dioperasikan oleh PLN, ya. So clearly these two have different missions, okay? They have different priorities, so they have different design philosophies. Okay? Just a hint. All right, any questions so far? Now let's take a look at one example here. This is a real cogeneration system, so I'm not making this up. These units do exist in PT Semen Padang, and actually they're not the only one that have this kind of technology. The ones that I remember clearly, PT Semen Indonesia's plant in Tuban and in Gresik, they also have this cogeneration in place. So it's not really that exotic, yeah. Okay, so this is not a novel technology by any means, but you know, it's a really nice and important thing to have in your chemical processing plant. Okay, and cement plant Okay, the reason why cogeneration is popular in cement plants around the world, not just Indonesia, is because cement processing plant is one of the most energy intensive process industry in the world, period. Okay, so if you compare, petroleum refinery, petrochemical complexes, actually they consume less energy per ton product compared to cement plant. Okay, jadi pabrik semen itu adalah salah satu kategori industri proses yang konsumsi energinya paling tinggi sedunia. Konsumsi energi per ton produk ya bukan total satu pabrik, itu kan tergantung dari berapa ukuran pabriknya. Tetapi kalau kita lihat berapa energi yang dihabiskan ya per ton produk, secara kategori pabrik semen adalah yang paling boros energi, ya paling banyak menghabiskan energi. Bukan boros ya kalau itu konotasi negatif ya, tetapi memang mereka paling banyak menghabiskan energi. And the reason for this high energy consumption in cement plants is because they need to heat, they need to burn, okay, they need to calcine or to burn their raw materials in the kiln at 1450 degrees Celsius. Yeah, 1450 derajat Celsius. That's an extreme temperature. Okay, and you need that extreme temperature to drive the chemical reactions that converts raw materials into cement clinkers. Yeah, that cannot be avoided. So the high temperature in the kiln here cannot be avoided, and that's the single reason why a cement processing plant consumes so much energy, because it operates at very high temperature. Okay. All right. So that means inevitably any cement processing plant will produce a lot of waste thermal energy, a lot of excess thermal energy from their rotary kilns. Yes, of course, this energy, this thermal energy, this hot gases coming out of the kiln is used to dry the incoming raw materials, to use to pre-calcine. Pre-calcine meaning it's oxidizing the raw minerals, okay, before it's sintered in the kiln. But even with these energy-saving technologies, there's still a lot of waste heat that will be otherwise ejected to the environment if we do not add further energy-saving equipment. Okay. So this one here again, let me show you. Jadi alat-alat yang dirangkai bersusun seperti unit-unit yang tampangnya seperti siklon kemudian ditumpuk ini namanya adalah pre-calciner. Pre-calciner kemudian ditumpuk-tumpuk dengan suspension preheater dan sebagainya. Bottom line ya, ini adalah rangkaian alat yang tugasnya adalah mengeringkan, memanaskan dan juga melakukan oksidasi awal terhadap bahan baku. Semuanya butuh panas. Dan panas tadi diambilkan hampir 100% diambilkan dari panas yang gas buang dari kiln. Oke, jadi ini sudah menghemat energi ya. Tetapi itu pun kalau nggak dipasang alat-alat waste heat recovery, ini pun juga pabrik semen masih akan memboroskan energi. Dia masih akan melepaskan CO2 dalam jumlah besar ke atmosfer. Ya. Karena itu sangat penting bagi suatu pabrik semen untuk memeras lagi, mengambil lagi energi di dalam gas buang di sini. Okay, and here. So there are two streams of hot gases that can be utilized to generate steam. Okay, which is from air quenching cooler. Okay, so this is the unit that cools down the clinker. Now imagine, you can imagine clinker as like these glowing hot pebbles. Okay, bentuknya tuh seperti kerikil yang agak besar dan ini membara panas sekali, masih membara panas sekali dan ini harus didinginkan. Ya. And the way we cool clinker is by using air cooler. So this cooler sucks air from the environment, and the air then is used to cool down quickly the clinkers. And in doing so, of course, you will end up with hot gas, hot air, right? So air coming out of the cooler will be hot. And that hot air can be used to generate steam because they're very hot. Okay, so the waste heat from the AQC boiler, from the air quenching cooler and from the suspension preheater is then used to generate steam, which in turn generates electric power. Okay. So that's a very nice way of utilizing, of minimizing waste heat. So wait, let me check where we are right now. All right, okay, good. So my plan today is to finish at slide number 9. So we are now at slide number 6. That's fine. That's all right. We don't need to push it if we cannot. Okay. Just feel free to jump in if you have any questions. Just interrupt me if you have any questions. Okay. Okay. The next one is now let's take a look at some more specific technology for cogeneration. So there are several ways to perform this cogeneration. The first one is using steam turbine. Okay, to be more exact, back pressure steam turbine. Okay, so back pressure steam turbine is one of the most commonly used work generation system in a cogeneration. Okay, the outlet steam from the turbine is from this turbine. Okay, is usually saturated or nearly saturated, and is used for process heating. Okay. Now, remember from your thermodynamics class or from our discussion on steam distribution system, if we want to use the steam for heating purpose or thermal steam, then it is the latent heat of the steam that we use, not the sensible heat. So a suitable state for a thermal steam is, of course, saturated or nearly saturated. Okay. Because we don't want the sensible heat. We want the latent heat of the steam to perform the heating. Okay. So here, what you see here, so the steam is fed to the steam turbine, and as it drives the turbine, it generates electricity. Okay. So this is an electric generator, and then the steam, the turbine outlet steam is used as a heating media. Okay. And this would be this is the process plant that receives the combined heat and power from the power plant. Okay, and typically a chemical processing plant still needs imported electric power. So it's quite rare actually to find a chemical processing plant that 100% generates its own electricity, its own heat and power. Usually there's still some imported utility from outside of the plant. Okay. All right, and this is very simple. And the weakness of this simple system is the interdependency between electrical and thermal loads. So this is the electrical load, right? This one and that one. Okay, and this one is the heating load or thermal load. Okay. And the reason why we have this interdependency is because, of course, because the steam, the thermal steam comes out of the turbine. So if there are changes, for example, if the load, if the electricity load increases, right? If this increases, then the turbine outlet steam will also change. The thermodynamic condition and the flow rate will change because of changes in electrical load. So we say that there's an interdependency between electric load and thermal load. There are some ways that we can reduce that interdependency, because interdependency is as a general rule, it will make your plant control system more complicated if you have interdependencies between streams. Okay, so we want to reduce that interdependency as much as possible. So we can do that, for example, by connecting the cogeneration plant to power grid, okay, jaringan distribusi listrik, yeah, that can go beyond the chemical processing plants, or it can also be connected to other power plants, for example, diesel generator. Okay, so this is the reason why we always need backup system, why we always need backup electric power generator to match these fluctuations in electrical load. Okay. Right. So you can see on the right hand side here there are several flows of energy. So number one here, cogeneration plant at one side set up set up for grid parallel import and export of electricity. The cogeneration plant supplies electricity to site across a single grid feeder, this one here. Okay, so in this scheme, the cogeneration plant only supplies its power to one site only. Okay, or it can export the electricity to grid distribution network, jaringan listrik. Okay, right. And once it goes to the grid, then the grid can help to level out the load. Ya, jadi kalau listrik itu kemudian masuk ke dalam jaringan, ke dalam grid, maka dia akan menjadi lebih stabil. Ya, karena kalau ada fluktuasi di dalam kebutuhan listriknya, fluktuasi tadi masih bisa diredam oleh grid, masih bisa diredam oleh jaringan listrik. Ya, mungkin di dalam grid ini ada lokasi yang sedang butuh listrik. Jadi dia bisa menyerap lebih banyak listrik yang dihasilkan oleh cogeneration ini misalnya. Ya, atau di sini memiliki buffer capacity. Okay. So an electric grid can also act as buffer. If there's some fluctuations in electrical load, it can act as buffer. So the power plant doesn't need to follow that fluctuation, on a very dynamic manner. Okay. Okay, and how actually we perform steam flow rate control in this cogeneration by using steam turbine. So the control of steam flow rate is done with, based on the measurement of steam pressure. Okay, so this is the control loop for the steam pressure. Okay, so as you can see here, this is a turbine, and then this is a bypass line. Okay, so this is a steam bypass line. So the steam is taken out before it enters the turbine. Okay, there's a junction here, and the amount of the flow rate of steam bypassed from the turbine depends on the steam pressure here in this line here. Okay, and this line so this steam goes to process. Okay, right. So if there's a steam deficiency in the process, okay, so if the plant needs more steam, okay, then the steam pressure decreases because more steam is being drawn by the process. Ya, jadi kalau kebutuhan kukus prosesnya naik, maka tekanan steam di sini akan turun karena lebih banyak disedot oleh pabrik. Ya, karena tekanan di sini turun, maka this PRV, pressure reducing valve, will open. Okay, right. So less steam here, decreasing pressure. It will be responded by the opening of the PRV, pressure reducing valve. Okay, and vice versa. Okay. If the steam requirement is decreasing, then this valve will close. Okay. Cogeneration with PRV is suitable if process heating steam requirement is larger than motive steam for power generation. Okay, so if this, in other words, in easier words, if the requirement of this steam here, the flow rate of the steam here is larger than this one, then this control system using PRV works. Okay, again, this type of configuration works. Okay, this type of configuration means that the turbine is a back pressure turbine. Yeah, and the steam flow control is done by steam bypass line to the process plant. Okay, so this configuration works if the steam flow rate here is larger than there. Okay, right. If the steam requirement for the process heating is less than motive steam from the turbine, then we use extraction turbine instead. Ya, jadi kalau ternyata kebutuhan steam pemanas di proses itu lebih kecil daripada kebutuhan steam penggerak turbine, maka konfigurasi ini nggak cocok. Yang cocok adalah kita menggunakan turbin ekstraksi, extraction turbine. So obviously, if we use extraction turbine, then the point at which we get the steam for the process is not here, but here from the turbine itself. Oke, ya saya ulangi dalam bahasa Indonesia. Jadi kalau kebutuhan steam prosesnya ini lebih kecil dari ini namanya thermal steam ya, ini thermal steam, yang ini namanya motive steam. Jadi kalau kebutuhan thermal steamnya lebih kecil daripada motive steam, maka ini nggak cocok konfigurasi ini. Yang cocok adalah menggunakan turbin ekstraksi. Nah, kalau kita menggunakan turbin ekstraksi, mengambil steamnya nggak di sini, mengambil steam untuk prosesnya nggak di sini, tapi keluar dari turbin, gitu ya. Okay, so again, it really depends on what's your priority. Does your plant requires more heating or more electric power, or perhaps balance? It will determine the configuration of your cogeneration system. Okay, baik, ada pertanyaan? Any questions? Okay, all right. If there isn't any question, tomorrow's class will be taught by Pak Hendra, so he will continue. He will pick up where we left off today. Okay, so and we're pretty sure that we can finish this rather short chapter this week. Okay, so we don't need more than 1 week to discuss cogeneration and combined cycle. All right. All right. Thank you very much, and we'll see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah.